Hi Calculus student, this video is for 5.1 part 2, approximating area. So on the last section we talk about sigma notation, and then this one we actually talk about how we can approximate area using small rectangles and introduce some standard notations. So what happened is I'm going to blow this up a little bit more. So assuming this is the function that we want to we're considering, it is f of x, and we want to approximate the area from interval a, close interval a to b. Okay, and we want to cut them into small rectangles. So first of all, we'll partition the x-axis from a to b into, so it seems like I'm putting them into 5 only, so but it could be ... in between. So what happened is the first one, because there's n rectangles, we would say each one of these supposedly equals equal width, and we want n subinterval, so this would be the width of each rectangle. So of course the width would be, because we want n of them, would be b minus a divided by n. You have that many length, that many inches, that many whatever, and you divide it by m. And we give them a special name. We call it delta x. Small change of x, because this is the x-axis. And we also label them in a certain way. We label the first one x sub 0, and the last one x sub n. Why? Because the second one is x sub 1, like this mark is x sub 1, and because there's n of them, so this is the first rectangle 1 on the right side is x sub 1, 2 on the right side is x sub 2, right? And then it turns out that the n one with the right side would be x sub n. Does that make sense? So the first one is x0. Okay, so and then each one of these the ith intervals, would have a lower limit of x sub, like say for example the first one, the x1 is on the right side, x1 minus 1 minus 1 8, which is x0. So we would have the I interval would have the left boundary of xi minus 1 and the right boundary of xi. Kind of like the second one, we have I, x1 and x2. The third one will be x2 and x3, right? You see how they have the left and the right interval. So the indexing of I, if this is the I interval, would have the same index as the right x notation. And we call each one of these a partition. And this way of partitioning the a to b is called a regular partition. If you are doing equal width, there are need for not doing equal width in like more complicated function, but for regular polynomial, equal width is fine. Okay, so that's how we want to partition our rectangles. Now we are going to look at two ways. I think in calculus 2 they will talk about more different way, like middle, a point of approximation, and others trapezoidal approximation. But for the most part, right now we are looking at only left endpoint approximation and right endpoint approximations. So what happens is, if I am to cut a rectangle, small rectangle from each of the partition, using each partition as the width, then I would use I need to pick a height of the rectangle. And if I do left endpoint partition, then the left boundary of each of the rectangle will be my height. So that means at we talk about at xi, at the I interval, the I partition, I have xi minus 1 comma xi, right? So f of x left side, f of I minus 1 would be my height. The height. And actually the first left height will be f of x0, right? x0 is my first height over here. So, and then I add so this is the height, this is the width, delta x. Delta x is equal for all of them, plus f of x1, delta x, all the way to n. Okay, sigma 1 to n. Right, from 1 to, okay, actually it's n minus 1, it's not n, because you start from 0, you should not add all the way to n. You, like, if you have 4 subdivision, you will from 0, 1, 2, 3 only, so up to n minus 1. And in your sigma notation, you will say sigma from I equal to 1. Oh, why do I want to start from 1? Because all my formulas start from 1, right? And then your f of xi minus 1 delta x. So this is the same as I equal to 0 to n minus 1, but we index it from 1 so that we can use those formula, f of xi minus 1 delta x. So that's the formula for left endpoint. The right endpoint is a little easier. Oh, I have this typo here. Okay, so, and then this is actually, this is from 2 to n. I should fix it. So on this partition, the function value on the right endpoint is the height. Remember, on the right endpoint, my I partition are labeled as what? Xi minus 1, comma xi, right? So the first partition would have x1 on the right side. The second partition have x2 on the right side. So remember? So I would just, the first one is f1, x1 times delta x. The second one is x2 delta x. The last one is xn delta x, right? So for right endpoint, the indexing is very good. It's just sigma I equal to 1 to n, f of xi delta x. So this is a very nice way of writing the area. So now this area is not the exact area under the curve, but it's a right endpoint approximation of the area. Okay, so let's use this notation and then try to do two example. One, the first one is my function is x squared, and I want to find the area under x squared from 0 to 2, and I want to use 4 subinterval, one from left side and one from right side. Okay, so I will use decimal to calculate all those f value. So what should I, maybe I'll draw the picture here. So f of x squared is like this, right? Use the picture. So this is the y-axis, x squared from 0 to 2, and because I'm using 4 endpoint n equal to 4, so I imagine my delta x would be what? 2 minus 0 over 4 is always, delta x is always, you have to remember this, b minus a over n. The upper limit minus the lower limit over the number of rectangle you're using. So that means it's 1/2. So each one of this width is 1/2. So I would have 1.5 and 1.5, right? So these are my x0, x1, x2, x3, x4. It corresponds to my labeling of the partition. And then, so I would say for the left 4, I start from the left side is f of x0. x0 is 0, right? So it'll be f of 0 times the height times the width. The width is delta x, which is 1/2. The second one is f of 0.5, because this is 0.5, right? Then it is 1, and then this is 1.5. It's very small. Times also delta x is 1/2 plus f of, so 1 and then 1, right? I get to 1 times 1/2. And then the fourth one is 1.5, right? Times 1/2. And then f of x is actually what? X squared. So it'll be 0 squared times 1/2 plus 0.5 squared, because my graph is x squared, times 1/2 plus 1 squared times 1/2 plus 1.5 square times 1/2. If you add these together, that is, did I add it myself earlier? Yes, I did. I got 1.75. Okay, what about right side? On the right side, you would think that the first one, I will start from 0.5. So I would say it is f of 0.5 times 1/2 plus f of 1 times 1/2 plus f of 1.5 times 1/2 plus f of 2 times 1/2. The last number is 2. So this is the rightmost one. So I have 4. 1 rectangle, 2, 3, 4. And so plug in here, that would be 0.5 square times 1/2. If you do it manually, 1 square times 1/2 plus 1.5 square, 5 square times 1/2 plus 2 square times 1/2. And if you do it manually, it's 3.75. Now you can help to generate this number by decimal again. So I'm going to show you. Okay, so you switch to decimal, and then you put x square here. You put x square, and you say, okay, this is x0. This is x1 0.5 because each one is delta x 0.5, and then add 0.5, add 0.5. So these are the x value. So that's h of x is x squared. So they square it for you, and then you just add this together, and then times 1/2. You get the answer. So you get it faster that way without doing your plug-in yourself. Okay. So this is one way. So we can do this one. I'm going to use the decimal to help me. My function is x squared minus x plus 2. So if I graph it, it's still like that. Okay. And I want it to be under from 0 to 4. I want 8 subdivision. So 1, 2, 3. Oops, okay, too much. Is enough time. How to erase it. Okay, try again. Okay, so this is 2, 1, 2, 3, 4. But I want 8, so each one would be what delta x is 4 minus 0 over 8. Oh, is also 1/2. Okay, so we want nice number. So you would imagine that your L left 8 would be again f of 0 first because you start from 0 times 1/2 because delta x is 1/2 plus f of 1/2 times 1/2 all the way to f of 7.5 only, right? No. 4, what is before 4? 3.5 only times 1/2. And you add them together and it turns out to be, I think I did it earlier, left side is 18.5. And how do I get it that fast? I use decimal to help me. Okay, so see how if I do it with decimal. So I put it over here. I put the function x squared minus x plus 2. I put all the x value, x0, x1, x2. Every time increase 1/2. And then this is f of x. They would tell me f of 0, f of 1, f of 2. And so I just copy this over, and then every one of them times 1/2, or I would just add this together times 1/2. That would be my left endpoint. And then how do I do my right endpoint? I start from 2. Well, okay, so I add all the way to 3.5, right? For the right endpoint, I start from x1, which is 1/2. So I was at 1.75 plus 2 plus 2.75 plus 14, and then times 1/2. So I hope you understand. So this is how I do it with the help of the graphing calculator to find approximate left endpoint and right endpoint. So for example 3, I'll do it in class. Okay.